Product notation basically shares the same it's the same idea as the summation notation. So it's a shorthand, but as the name suggests, okay, it's a product. Okay, so we use the Greek letter pi, okay, to represent product. So for example, you can see that over here we have the product of k equals to 1 to n for ak. So essentially everything is the same. We have a lower limit, upper limit, we have the explicit formula or the particular terms that we want to multiply together. Okay, the only difference is that for sigma is sum, for pi is a product. Okay, so instead of adding, we now multiply the terms together. So we start from the lower limit a1. Okay, so we have a1 times a2 times a3 all the way to times an. Okay, hence uh, okay, the product of k equals to 1 to n for ak is a shorthand for the product, okay, of a1 all the way to an. Okay, so in general, the product of a sequence of terms am plus 1 am plus 2 and so on, right? Okay, is denoted by the pi notation. So pi k equals to m to n for ak. So just like for sigma, okay, we have the lower limit, we have the upper limit, and we have the index, okay, or the counter in this case. So our counter is k, our lower limit is m, upper limit is n. Okay, so just like for sigma notation, okay, it's also possible to separate off the last term, as you can see here. Uh, Finding the last term basically involves the same skill as finding a last term for the summation notation, except that if it's a sum, what we do is we find the last term, we add it back in, so it will be a plus here. Okay, but in this case, because it's a product, so after you find the last term, you multiply it. Okay, so it's actually we use a dot to represent the multiply in this situation. Okay, so you can basically apply everything that you have learned for section 2.0, which is on summation, into the product notation. So example, okay, we can compute the product for this given pi notation. So you have index k equals to 1 to 4. You are doing the product for k plus 1 divided by k. So we start off by substituting the index k equals to 1 into the explicit formula k plus 1 divided by k. So you have 2 over 1. Okay, then we sub k equals to 2 into the same formula. You have 3 over 2, k equals to 3, k equals to 4. Okay, so that's your product. Of course, because there's no unknown, so you are expected to work out, okay, for the final answer. Good thing about fraction product multiplication is that you can do a lot of cancellation. So in this case, 2 and 2 we can cancel, 3 and 3 we can cancel, 4 and 4 we can cancel. So end up with 5 divided by 1, which is actually equals to 5, right? So here we have two exercises. Okay, you have first one, k equals to 3 to 5 for bk. So this is a situation where individual terms, value of the individual terms are given as part of the question. So you see b3 is minus 3, b4 is 8, and b5 is 100. Okay, you're supposed to compute k equals to 3 to 5 for product of bk. So 3, 4, 5, there are total 3 terms. So we have b3 times b4 times b5. Okay, so it's a negative 3 times 8 times 100 gives you negative 2400. Okay, part B, you have a product of k equals to 3 to 4 for bk plus 1. So in this situation, we sub k equals to 3 into the term, you have b sub 3 plus 1, which is actually equals to b4, okay, times b sub 4 plus 1. So you have b4 times b5, which is 8 times 100, okay, gives you 800. Okay, next compute the product of k equals to 4 to 5, okay, for k plus 1 divided by k minus 1. Okay, so just like in the situation for summation, because this minus 1 is not involved, okay, it's not part of the product notation, there's no brackets here, so we only do the minus 1 one time right at the end. Okay, so we sub k equals to 4 into the explicit formula. You have 4 plus 1 over 4, which is 5 over 4, and sub k equals to 5 into the formula. You have 5 plus 1 over 5, which is 6 over 5. Okay, notice that we do the minus 1 only one time outside the product. Okay, so 5 and 5 we can cancel, so you have 6 over 4 minus 1, which actually gives you 1.5 minus 1, so answer is half. Okay, so be careful, the the -1 is not included as part of the pi notation, right? Okay, next, evaluate k equals to p plus 2 for k over k plus 1. So this is a situation, once again, that we work with uh, unknowns, okay, rather than work with actual numbers, but it should be the same concept. So our lower limit is p, upper limit is p plus 2. So after p should be p plus 1, then p plus 2. So you know total you have 3 terms, okay. So our first term, we sub k equals to p into the formula, you have p over p plus 1 times, okay, then we sub p plus 1 into the formula, you have p plus 1 over p plus 1 plus 1, which is p plus 2, okay, times p plus 2. Okay, so we sub p plus 2 into the formula, you have p plus 2 over p plus 2 plus 1, which is p plus 3. So likewise, in this case, you can do some cancellation, okay, and simplification of the product. So p plus 1 and p plus 1 you can cancel off, p plus 2 you can cancel off. So answer is just p over p plus 3, right? Okay. We are also expected to be able to do the reverse. That means, given a product, you are supposed to be able to express it using the pi notation. So in this situation, we have 1 times 2 times 3 times all the way to times n minus 1 times n. Okay, you are supposed to express this using the pi notation. So same thing, what we do is essentially we look at individual terms, ask ourselves how is it related to our index, okay. What changes, okay, across term 1 to term 2. So you notice that term 1, okay, is basically just equals to 1, so we have k equals to 1. Term 2 is k equals to 2, term 3 k equals to 3, and the final term is actually k equals to n, okay. So explicit formula is just expressed as k, okay. So what is our lower and upper limit? Okay, we start with k equals to 1, we end at k equals to n, so it's 1 to n. Okay, so expressing this product using the pi notation, you have okay, the product from k equals to 1 to n for k. Okay, our formula is just equals to k. Okay, this is also called, you can read it as n factorial, you can express this as n factorial. We will learn more about this in CMATHS2. Okay, so it's a n factorial can be used as a shorthand for product of 1 to n for k. Okay. Uh, So next, okay, you're asked to rewrite uh, a product of k equals to 1 to n plus 1 for 1 over k plus 1 by separating off the final term. Okay, so essentially we use the same skill. Okay, you start off by expanding this. Okay, then you try to express the first to the second last term, okay, using pi notation, and multiply the last term, the final term back, okay, to maintain the equality. So let's expand this. Okay, our lower limit is k equals to 1. So index, first index will be k equals to 1. Sub into the formula, you have 1 over 1 plus 1. Then you have k equals to 2, so 1 over 2 plus 1, k equals to 3, 1 over 3 plus 1, and of course this will go on. Okay, then we look at the second last term. Okay, now our upper limit is n plus 1, so the term that is just before n plus 1 will be n, k equals to n. So we substitute k equals to n into the formula, you have 1 over n plus 1, and then the final term will be k equals to n plus 1, so we substitute n plus 1 into the formula, you have 1 over n plus 1 plus 1. Okay, so we want to separate off the last term. In other words, we want the first term to the second last term to be expressed using the pi notation. So not difficult to do this. You can basically read off everything from here. The only thing that changed is the upper limit. Okay, so the lower limit k equals to 1. The formula is 1 over k plus 1. We duplicate it here. Okay, the only difference is for the original pi notation, our upper limit is n plus 1. Right now, because we want to exclude the final term, so our upper limit is n. Okay, so obviously now they are not equal. You need to do something here to maintain the equality. So what do? We basically need to multiply the final term back. Okay, so we include the final term with a multiplication. Okay, and of course we do some simplification. N plus 1 is actually n plus 2. So that's how we separate off the final term. Okay, uh, you can also change the variable, which we cover in for the summation notation. So what is involved in change of variable is that you need to compute the new lower limit, the new upper limit, and the new formula by utilizing the relationship given. Okay, so this is the original product notation, k equals to 2 to 4 for k squared. Okay, the relationship between our old index, which is k, and our new index, which is p, is that p is equals to k plus 2. So we use this to compute the new lower and upper limit. So when k equals to 2, this is our original lower limit. Okay, p will be sub 2 into here, so you have 2 plus 2 gives you 4. So p equals to 4 is our new lower limit. Okay, our original upper limit is when k equals to 4. So when k equals to 4, you sub 4 into where k is. Okay, so you have p equals to 4 plus 2, which is 6. So p equals to 6 is our new upper limit. Okay, so since p equals to k plus 2, we express k in terms of p. We bring the plus 2 over to the other side. K equals to p minus 2. So we sub k equals to p minus 2 into our original formula. Okay, uh, what we have is that k squared, which is our original explicit formula, now becomes p minus 2 whole thing squared. Okay, that's our new formula. So you have the new lower limit, new upper limit, and the new formula. Okay, you should now be able to express the pi notation, okay, in its new form. Okay, so this is the old form, is equals to p equals to 4 to 6 for p minus 2 whole thing squared. Okay, so this is rewriting by changing the variable. Of course, you can perform a check. So right hand side, if you were to expand it, you will get 2 square times 3 square times 4 square. If you were to do the same for the left hand side, you will find that you will get the same answer.